Hi everyone, today we're going to derive a net ionic reaction, paying very close attention to the procedure by which we can derive the net ionic reaction. So we're going to follow a very careful 4-point step-by-step procedure. The first step is going to be to determine the molecular reaction. Now, in order to determine the molecular reaction, we need to know the formulae of both the reactants and the products. It's very important to keep in mind that the formulae are determined by the charges on the ions. And so we'll go through how we can do that to predict what they are. But remember that the charges on the ions determine the formulae, not the numbers of ions in the reactants. Once we have the formulae, then we can balance the chemical reaction. With the balanced chemical reaction, we can then apply solubility rules to determine which of the reactants and products are going to dissociate and which may be insoluble. Once we know that, we can write the total ionic reaction, indicating which ionic species have dissociated to form ions in solution. Once we see the ions in solution, we can determine which are the spectator ions. These will be the ones which remain chemically unchanged as the reaction progresses. Once we know the spectator ions, then we can write the net ionic reaction. Okay, so let's apply that to a simple example, the reaction of sodium phosphate with calcium chloride. So the first job is going to be to determine the formulae of both the reactants, which are given here in the title, and also of the products, which will be the reaction products for the double replacement reaction. So we'll ask the first question, what are the formulae of the reactants? Well, let's start by listing the ions that are involved. So we have sodium. Sodium is in group 1, or group 1A in the older nomenclature of the periodic table. Sodium ions form ions with a +1 charge. Phosphate ions, we know because we've memorized them, phosphate ions have the formula PO4 with a 3- charge. Calcium, atomic number 20, is in group 2A in the older nomenclature, or column 2 of the periodic table. Calcium ions form with a charge of 2+. And then chloride. Chlorine is a halogen, so the anions of halogens all have a -1 charge. Chloride has a minus charge. Okay, so now we can put these things together to form our reactants, starting with sodium phosphate. Since phosphate has a 3- charge and sodium has a +1 charge, it's going to take 3 of the +1 charges to cancel the 3- charges from phosphate. And so sodium phosphate has the chemical formula Na3PO4. 3 sodium ions, 1 phosphate ion. Calcium chloride, on the other hand, it's going to take 2 of the negatively charged chlorides to balance the charge on the calcium. So calcium chloride has the formula CaCl2. Now, those are the reactants. What about the products? Let's take a look at the products. The products of the reaction are going to pair sodium with chloride. Sodium has a +1 charge. Chloride has a -1 charge. They can combine in a 1-to-1 ratio to cancel those charges out, and so sodium chloride has the formula NaCl. The other product is going to pair the calcium with the phosphate. And now this gets a little bit more complicated. Calcium with a 2+ charge and phosphate with a 3- charge. We're going to have to find the least common multiple between 2 and 3. That happens to be 6. So to get a total of +6 due to the calcium, I'm going to need 3 calciums. And in order to get -6 due to the phosphate, I'm going to need 2 phosphates. Notice how the 2 and the 3 come into play in the chemical formula. It takes 3 calciums for 2 phosphates. And also notice the use of the parentheses to determine the phosphate as a single ionic group. So the chemical formula for calcium phosphate is Ca3PO4-2. Once we have the reactants and the products, we can now balance the molecular reaction. And so there we go. Here are the reactants. Here are the products. And so when I look at this, I see, uh-oh, I'm going to need 3 calciums. I better put a 3 here. That's going to give me 6 chlorines, so I better put a 6 in front of the sodium chloride. That's going to give me 6 sodium, so I better put a 2 here. That gives me 2 phosphates, which is the correct number. So there's the balanced chemical reaction with all of the correct stoichiometric coefficients in place. Once we've gotten to this point, now we've completed the first step. The second step was to use the solubility rules. So the solubility rules, what we're going to do is take a look at each of the species. Sodium phosphate, for example, we know is soluble because sodium, being in group 1A, forms soluble ionic compounds. So ionic compounds with sodium as an ion are going to be soluble. Secondly, calcium chloride we know is soluble because chloride salts are soluble. And calcium is not among the exceptions to make chloride salts insoluble, so this is going to be soluble. Sodium chloride has 2 rules going for it. It's a sodium salt and it's a chloride salt, so it's going to be soluble. Calcium phosphate, on the other hand, has a phosphate ion, and phosphate ions are insoluble, so this is going to be insoluble. So we can determine the solubilities using the solubility rules as presented in class. Phosphate ions are soluble if they're paired with group 1A ions, such as sodium. That's why this was soluble, but this one here is not. So now, once we know which are soluble and which are insoluble, we can now write the total ionic equation by taking into account the dissociation of these compounds to form ions in solution. So let's start with the total ionic reaction by separating those species that are soluble. So starting with the reactants, we see that sodium phosphate was soluble, so it's going to break up into sodium ions and phosphate ions. Calcium chloride was soluble. It's going to break up into calcium ions and chloride ions. Notice how the coefficients are now multiplying the ions. On the product side, sodium chloride is soluble, so it's going to separate into its constituent ions. Calcium phosphate, however, is insoluble, so it's going to fall out of the solution mixture as a solid precipitate. So we don't dissociate that, we don't write it dissociated, we indicate that it is going to form a solid. Now, once we look at this total ionic reaction, now we can remove any ions that have been unchanged chemically as the reaction progresses. So one obvious choice is sodium. We have 6 aqueous sodium ions, and we ended up with 6 aqueous sodium ions. That's no change. So we can eliminate sodium. Boom, there it goes. And also we can eliminate chloride, which has 6 aqueous chloride ions and 6 aqueous chloride ions at the end. So, boom, there it goes. What remains is now the net ionic reaction. So we've removed what are called spectator ions. They simply watch the chemistry happen, but the chemistry is happening between calcium ions and phosphate ions to form the insoluble precipitate. So now we can write the net ionic reaction. We eliminate the spectator ions, and what we have left is the net ionic reaction. The net ionic reaction shows the reaction of calcium with phosphate to form calcium phosphate. And notice how the stoichiometric coefficients for the separated ions have now become subscripts in the ionic compound for the solid. The spectator ions in this case were sodium and chloride. They were removed from the net ionic reaction. So, in summary, we determined the formula for the reactants and products using the charges on the ions as a guide. Next, we balanced the chemical reaction, the molecular reaction. Third, we used the solubility rules to determine which species will dissociate and which will not. Fourth, we wrote the total ionic reaction, canceled the spectator ions, and finally, what was left over was the net ionic reaction. So I hope that this summary has been helpful. And good luck to you as you derive net ionic reactions in the future.